Hi everyone, today we're going to be talking about topic 3.13, Beer Lambert Law. This is the last topic in Unit 3. So we've been spending a lot of time talking about spectroscopy and using light in order to analyze details about different solutions. And the way the spectroscopy works is through what's known as a spectrophotometer. And so in a spectrophotometer, you have some sort of a light source that'll send your light through a glass here. That'll focus it into what's called a monochromator. And this will take your white light and then split it into all of its different wavelengths of light. And so you can see a red, orange, yellow, green, blue, and violet there. What it'll then go through is a wavelength selector, which is basically just a piece of metal or glass that has a small little hole in it. And it's just select for whichever wavelength you want. So this can move up or down. If you want violet, for example, that slit moves down and only lets the violet light in. That light will then go into your solution, which is what's inside of what's known as a cuvette. Your solution will absorb the light. You'll measure the intensity of the light before. So I naught or I0 equals intensity before. And then you'll measure the intensity afterwards, which we call IT, and this is the intensity after. This will then go into your detector, and then you'll get a reading of the absorbance on some sort of a display meter. So now we're going to spend a little bit of time remembering our art classes and thinking about color theory. And so solutions can be all different colors. So when taking a absorbance spectrum, different wavelengths of light must be used. Now, something we need to remember is that, for example, if a solution appears red, so as in if you look at a solution and it's red in color, that means it reflects red light but absorbs all other light. And so oftentimes you will use complementary colors. For your wavelength. So if something appears red, for example, you would want to use green light to excite it. And so what we're actually doing when we use a spectrophotometer is we are measuring the light that is absorbed by a sample. And we call that measurement the absorbance. And this actually is unitless. Absorbance doesn't have any units associated with it. Higher concentration generally equals higher absorbance, which equals more intense color. So if you have a red solution that's really, really concentrated, you'll have a higher absorbance. But if you have a red solution that is, really see-through and you can't really see the color that much, that means it has a low concentration and a low absorbance. And this is because more concentrated means more densely packed particles. And so more light is absorbed. And now, as a reminder, right, concentration is given in molarity in this instance. And so molarity is moles solute over liters solution. Now, spectrophotometers don't directly measure absorbance. And sometimes you'll see me label absorbance as ABS, ABS, just because it's a little bit easier and faster to write. Instead, what it measures is transmittance. In transmittance, is the amount of light that passes through the sample. The way that's calculated, transmittance, or otherwise known as T, is equal to IT over I0. So I0 is equal to light intensity before it hit the sample. So that would be this part right here. If this is your sample, that would be I0. And then IT is the light intensity after. So once it's reached the sample, that would be IT, I0, just like it says in that diagram. Now, transmittance isn't really the most useful measurement for us to use, and so we're instead interested in the absorbance, which is the amount of photons absorbed by the solution. So the way you calculate that is absorbance, or A, is equal to the negative log base 10 of the transmittance, T, which is equal to minus log base 10 of IT over I0. That's how you would calculate the absorbance. Now, the reason why we really care about this in the context of solutions is because I said earlier that absorbance goes up as concentration goes up. In other words, absorbance A is proportional to concentration. And so if we know something about the concentration of a solution, we can infer how much light it's going to absorb, or if we know how much light a solution absorbs, we might be able to figure out its concentration. And that's where the Beer Lambert Law comes in. The Beer Lambert Law says that absorbance, or A, is equal to epsilon, the Greek letter E. I'm going to write that a little bit better. Epsilon B times C, where epsilon is equal to what's known as the molar absorptivity. Its units are liter times mole to the minus 1 times centimeter to the minus 1. Oh, let me write that a little bit better. Centimeter to the minus 1, or liter per mole per centimeter. And this is different for every compound. And so you'll typically be given molar absorptivity, or you can calculate it from absorbance and concentration. But molar absorptivity differs for every single compound. So it's not just one number that you use, similar like the ideal gas law, right? R is always the same no matter what. Epsilon, in this case, the molar absorptivity constant, changes depending on what kind of molecule you have. B is equal to the path length, or this is just the length of the container, which is normally what's known as a cuvette, which we'll be using in a lab quite soon. And so the path length is just the length of the container that your solution is in, and then C is your concentration, typically in molar, or, of course, moles per liter. And so using this, if you're given the absorbance, you can calculate a concentration, or if you're given the concentration, you can calculate the absorbance, assuming that you know the molar absorptivity of your material and you know the length of the container that you measured the absorbance in. So the way this works experimentally is that you would first run a blank of just solvent. And so you would just measure how much light your solvent absorbs. Then you would place your sample in a cuvette, then in the spectrophotometer, and then you would just test absorbance at your wavelength of interest. So if you see here in this graph, this is a typical spectrum you'd produce by looking at all wavelengths, but you would take absorbance readings at a whole bunch of different wavelengths, and then you'd find where that maximum is right there. And so you can see we have maximum absorbance of about, 0.45-ish at around 525 nanometer. And so that's how you would essentially figure out where your maximum absorbance is. And we should always use wavelength that gives maximum absorbance. Once you've done that once, you can collect data at multiple concentrations, and then you construct a calibration curve. Now, this is a little bit misleading because this should be linear. It isn't really necessarily a curve, but what you do is you plot your concentration of your sample versus the absorbance at each concentration. You do this multiple times. So here we have standard 1, 2, 3, and 4. And what you'll do is you should generally conserve a linear plot like this, where now, of course, you might be able to see, right, if here we have absorbance and here we have concentration, this line here, the slope is equal to epsilon, or the molar absorptivity. And so one way you can find the molar absorptivity is just by taking a sample at multiple concentrations, measuring the absorbance at each concentration, and plotting it as a calibration curve. As long as it's linear, that slope is your molar absorptivity. And what you can do from this, which is really interesting, and the reason why we actually want to do a method like this, is you can measure an unknown sample containing your compound of interest, you will get the absorbance, and then from that you can find where it falls on your calibration curve, or using the molar absorptivity that you found from your calibration curve, you can calculate concentration. So I have an unknown solution, but I have a calibration curve of that solution absorbing a particular wavelength of light. I can figure out how much or what concentration of my compound of interest is in that solution, and that's why we really care about this relationship. Now, I also do want to spend a little bit of time just talking about the lab technique and how we can create these standard samples and do these dilutions the proper way to make sure that we get really good calibration data and can get a good calibration curve. For two reasons. One, just so we know the best practices, and two, because this is really what we're going to be doing in our next lab, and I want to make sure everyone kind of understands what we're looking for. And so first you would mass out your compound of interest. For your stock solution, this is your solution of known concentration that you start with. This typically has a high concentration. Then you add sample to a volumetric flask, which we haven't covered that so far, but this right here is our volumetric flask. It's really the most appropriate flask for trying to make a standard solution like this because it measures volume very, very accurately. And so you'd add sample to a volumetric flask, then add solvent to the mark. And this will make your stock solution at a known concentration. Once you've created that stock solution, what you can do is create standard samples using what's known as serial dilution. Or in other words, dilution in a series. So rather than just picking 5 concentrations and saying I'm going to take from my stock solution and dilute that using my equation M1V1 equals M2V2, what you instead do is you take your stock at a known concentration of C. You'll take a little bit of this, throw it in there, and then you dilute. And then what you do is instead of taking from this stock, if you want to make your stock solution 2, and so this will be at concentration, the stock will be at concentration 1, your first diluted will be at concentration 2. Your second one, you'll take from this one and dilute there. And you will continue on and on. And this method just creates much less errors. And so rather than diluting your stock solution to every single concentration that you want, you will instead take a little bit from each dilution that you make and then add that to a new container and then dilute to your desired volume for your new concentration. This is just a much better way to do it that doesn't cause as many errors. One important thing here that you may notice is that your moles of solute never actually change. And so you'll always know how many moles of solute you have in there because all you're doing is you're changing the bottom part of our concentration equation. You're just adding more volume, essentially. You're not changing the number of moles necessarily. And so if you're trying to make a standard sample in order to construct a Beer Lambert curve, this is what you would do. We'll talk a little bit more about this as well as doing some practice problems and just general lab techniques in our next class. Otherwise, thanks, guys.